Hello. So today we are going to take a look at this problem called number of good leaf node pairs. And the problem is just that we want to calculate the number of good leaf pairs in a tree. And what we mean by good leaf pairs is just two leaf nodes that where the shortest path between them has a length smaller or equal to some given distance. So basically we get a tree and we get a variable distance, and we want to find the number of pairs that are leaf nodes that have the shortest path between them of length less than or equal to distance, right? So if we take an example here, like this tree with this row to node 1, the left node 3, right node 6, and 3 has a right node 5. And if the distance is equal to 3, what the answer here is that, well, for example, the only two leaf nodes we have are 5 and 6 here, and the distance between those is 1, 2, 3. It's exactly 3, so that's the only answer we have, and so we return 1. There's only one pair that has the property that we are looking for. In the second example, we have a tree like this, and the distance is still 3. So we have 4 leaf nodes, right? But the only ones that have distance smaller or equal to 3 are 3 and 4 and 8 and 9, because the distance between 3 and 4, that's just 1 to go up to 2 and then 1 to go down to 4. So that's just 2. So that fits the definition of being less than or equal to distance. So we count that one. And then we have this one between 8 and 9, which is just 1, you go to 5, and then another one you go to back to 9. You go down to 9. And so we have that one also has distance 2. And those are the only ones, because if we take, for example, 3 to 8, you'd have to go to 2, and then to 1, so that's 2, and then to 5, so that's 3, and then to 8, that's 4. So that's bigger than the distance, so we don't count those. So we have just 2. So this is the problem. Now let's take a look at how we can solve. Okay, so let's see how we can solve this problem. So the main idea here is to use DFS in this problem. So just using DFS and using specific DFS on this tree, we can use post order, which basically means we are going to process the child nodes and then process the parent. Because why is that? Because the state that we want to return to the parent is like how many leaves, like what's the distance from the node to the leaves underneath it, like all the distances. What do I mean by that? So let's take an example. Let's take like 1, 2, 3, the second example we had earlier, and then we had 5, 8, 9, something like this. So what we can do is have each node return to its parent the distances from it to the leaves underneath it to the parent, and the parent can just add itself to it. So let's just write this down so that we can kind of process it better. So each node returns to its parent the distances from it, a list of the distances from it to each leaf underneath it. Right? There is the special case of what if the node itself is, what if the node or the child is a leaf, right? Then at that point we can just return. This is kind of our base case in a way. Then, well, the distance is just 1. If I'm here and I'm asking the distance from me to this leaf node, that's just 1, right? And then if we do that, the solution becomes really easy. For a specific node, so for a node, we will get like the left distances, which are the distances from on its left, for its left child, the distance from its left child to leaf nodes, right? And then we will get right distances. which are the distances from itself, from its right node, right child, to the leaves underneath it, right? So once we get these two, we can just take each, so this would be a list, right? List of values, right? And same thing here, some list of values, right? So we could just pair them up together, right? And check each of these distances and add them up if they are less than, so let's call these L in this range and R in this content here. So it would be just taking all those that are, the count of those that are less than or equal to the distance that we get as a parameter, right? If you kind of conceptualize this, what does it look like? So you have a node here, and that node has a child, right? And if we are looking at this node, well, it maybe has a node here, and then two nodes here, and at this point we want this path here. But maybe also you have like a pair, something like this, right? And then this. So you want to pair this with this one here, and then you want to pair this with this one here. So each distance that you get from your left child, you want to pair it with each distance that you get from your right child, and for each pair, check if it verifies the property that we have. If it is, we add it to the total count. And we do this at each level, because for this level, we have some pairs, and then for this level, we have also some other pairs that go through this, like this maybe, and if we have like if we have some other nodes here, right? And so this is this here, the distances would be what our DFS method returns. So basically what this would mean here is, let me just write this here. So DFS return would be the distances from a node to leaves, to all leaves underneath it. So list of distances from a node to all leaves underneath it, leaf nodes underneath it, including itself. Like if itself is a leaf, we could just return this list one here. And so pretty much now we can write our DFS, right? We know the base case, and in general, recursion for a tree is just you recurse on the left side and the right side, and we know what the function should return. And so this is pretty much all we need. And so if we write this down, this would be DFS. First, let's just write the general function. So our general function would be count number of pairs. And we get the root, and we get the distance, the limit distance. And now we are going to write our DFS that we are going to call. So our DFS would be, we would just need a node, right? We have access to distance. And what is the base case? So we know that one of the base cases definitely is when, what we said here, when the child is a leaf. So a child is a leaf if it doesn't have a left child and it doesn't have a right child. Okay, in that case we said, well, the distance is just 1, so we could just return 1. But we want to return it as a list because we want to add it, since the result of the final DFS has to be a list of distances. And so we can just return a list of 1. Now there is an additional base case that I didn't mention earlier, which is what if we just get an empty node, right? It's just called null, so an empty tree. So we need to handle that as well. So for that, there is no distance, so we can just return an empty list, right? Now we need to do the recursion, like dividing for the recursion here. So we need to have the left distances, as I mentioned here, and the right distances, and we can pair them up. So we need the left distances, which would be just by calling DFS again on the left child, and the right distances, which would be calling the same function on the And since we are doing a post-order traversal here, we will process the node only after doing the DFS call on the children. And processing the node is exactly this pairing here to know how many valid pairs we have, right? And so that would mean that we will need some kind of count here, but that count counts for all calls to the DFS, so it's need to be outside this function. So let's just have something here in Python self.count so that it's global for all the calls to DFS. Maybe let's put it to the bottom a little bit more. So this would be self.count equal to 0. And here we want to process the leaf node. We want to process the node, right? This is pre-processing. Process the left child, right child, and then the node. And processing here just means we want to take we want to add up all the children so we want to count all the occurrences of pairs that have sum smaller or equal to distance. What is L and right? That's just the values of the left distance and the values of the right distance. We are just pairing up these two. So pair this and this one, which is L and R, and check if the distance is, if the sum is smaller than the distance. So basically what we are saying here, if we have something like this, this would be L, this would be R, right? So if you have a node, this distance here is L, and this is here is R. And if we have like another subtree, let's say maybe something like this, right? And something like this for each side, well, we want to as well pair this left with this R. Let's call this maybe R2 and this R1. So we want to L1 and this L2. We want to pair L1 with R1 and pair L1 with R2 because that's also a path. And we want to pair L2 with R1 and L2 with R2, right? So that's what we are doing here for. So that means here we will need to do for L in left distances and for R in right distances. And once we sum them, what should we return? We said that each function should return the list of distances from node to all leaf nodes underneath it. So what this would mean here is that we can return C plus 1 such that C is just the left distances, is in the list of the left distances plus the right distances. So why C plus 1? So if you have a node like this and it has a subtree and this one has another subtree, what should this parent know about this one? It should know all the distances that it has from all its leaf nodes. Well, the leaf nodes of this one are the ones here and the ones here. And so we want to take them all into account and add 1 because that one represents the edge between this node and its child. And that's what we need to return to the parent to take into account. And so that's why we take both. Let me just explain it again in case it's not clear. So if we have a node like this and then we have a node like this, right? And this node has a tree, let's say a left child that has another subtree underneath it. This one has a right child that has another underneath it. So this one returned to its parent all the distances it has for all the leaves underneath it. And the same thing did this one. And this one, in order to compare against whatever is here, needs to know all the leaf nodes underneath this one. And all the leaf distances from all the leaf nodes under this one are the leaf nodes under its left and those under its right, which is why we are taking both lists here. And we are adding 1 for this edge here. For each use case. For the left side, this edge here, and for the right side, this edge here. So that's why we are doing C plus 1. And then once we do that, we need to call the DFS here. So the DFS, we need to start the call by calling it on root. Just start from here and let it do post order traversal to get it for all the entire tree, right? And then at the end we want to return the self.count, because that's what the step we are doing here in the post-order traversal, to get at each node if there is a path going from it that constitute a short path distance less than or equal to distance from two leaf nodes, right? And we can just return this. There is small optimization that we can do here, which is here for C+1, if, let's say, the distance is equal to 3, right? And then, let's say this node here has these children of size 2, and this one of size 2, right? So that means that overall, in order to pass by this, you would have only something bigger than 4, right? So we already know that no matter what, we won't find something smaller than or equal to distance, right? So we just can disregard this and try to just look at the right side, right? And the same thing if we had 1, 2, and 1, that means this 3, that means if you try to look here, you will certainly have at least 4, right? So that means that here we can prune early and just take this into return the distance only if it's smaller than distance, right? Because if it's equal to distance, we would have to add another edge on the parent, and that would make it bigger than the distance, so it's not useful there. If it's already bigger than distance, same thing, that's not useful either. So we can just prune early here. And yeah, so that's pretty much it for this solution. Just simple DFS post-order traversal. The main challenge is to find this state that each node should return to a parent, which here is just the distance from the node to all its leaf nodes. And each node can process that because each node knows the distances on its left, the distances on its right, and can pair each of the two variants, as we said here, and check if it's lesser than or equal to distance. If it is, count it. If not, don't count it. And that's what we are doing with this sum here. Yeah, so let's type this down, test it on some examples, and make sure it works. Okay, so I typed down the solution here. So we have a tree node here, the value, and the left side on the right side. And the first example here is the example that we saw here, which give us 1. So we are starting for 1 here. So let's just see first what the tree will look like. Sorry, we just expect 1 here. Let me just comment this out. And the test passes. For the second example, which is this one here, we expect 2. And this test passes as well. This is just a tool that converts a string array to a tree. Yeah. Okay, so if you just take a look at the tree here that gives us the value 1, just to make sure. Okay, so you can see here the tree has 1, 3, 6, 5, and the answer we should get for distance 3, we only have 2 leaf nodes, so we should get only 1 answer, and that's what we are getting here. For the second tree, let me just draw. So this is just a utility here that will allow me to draw an array, a representation of a tree as an array like this, and draw it as a tree. So if we run this again, so you can see this, this example here, not this one. Let's run it again. So you can see we have 6. Yeah, let's draw this tree instead, sorry. The second tree, since we already looked at the first one. So you can see here we have all these leaves, and this is the same example we saw earlier here. And so we have these 4 leaves, but for distance 3, we just have 3, 4, and 8, 9. So that's why we should return 2 here. And if I run the assert, it passes, right? Yeah, so we can run on more examples, but it should pass for all of them. And the main idea is just, to summarize, is just use DFS with post order and let each child return to a parent the distances, a list of distances it has with the leaves underneath it, including itself, and the parent can just pair up the left side counts with the right side and check if the distance will give us, the total will give us less than or equal to distance. If it is, we count it. If not, we don't count it. And yeah, and return the answer up to the parent, and we return the overall count at the end. Yeah, so that's it pretty much for this solution. Next, we will look at a little bit of a different solution that instead converts the tree to a graph. Okay, so now let's see how we can solve this using a graph. So the solution using a graph is pretty straightforward. The steps we will do are the following. So the first step would be to just convert the tree into a graph. And then after that, what we will do is find the leaf nodes. So find all leaf nodes. So that can be easily found by just going through the keys of the graph and checking for each one. Does it have a left? Does it not have a left and the right child? If it doesn't have them, then it's a leaf node, and we can add it to the leaf node set. So here we get a graph map that is from nodes to their neighbors, and here we get leaves, right? Just a set of leaves. This third step here would be for each leaf. So for each leaf that we get from step 2, we can do BFS, right? And the goal here from doing BFS, since BFS goes level by level on the graph, we'll be able to every time to tell, like, is this level 1, is this level 3, 4, right? And then just pretty much check if the distance from each leaf, so we will be starting from leaves, right? And so maybe I should instead write this differently. So we will have maybe something that was a tree, but now it's a graph, right? So it will be like drawn something like this. And so we'll start from this leaf, for example, and we will go level by level. So this would be level 1, level 2, 3, 4, right? And so if we reach another leaf here or here, then at that point we have a distance between two leaves, right? So we would have the distance between a leaf and another leaf, like a pair of leaf nodes. And so there we could just check, is the length of this, is it less than or equal to the distance we are looking for? If it is, we can add it to the count, right? So all we need to do is find the other leaves that are not the same leaf as this one, and that are within this distance, like the level is within this distance, and that's pretty much it. And if it is, we can just add to the count. And so for each leaf, do BFS and find other leaves that has shortest path, since that's what BFS gives us. Let's call this maybe this leaf L1, right? And this would be L2. That has shortest path, less than distance or equal to distance. And of course, we want L1 to be different than L2, right? It's different than L2, right? We don't want to kind of go back or something similar to that. We want two different leaves, and the distance has to be less than or equal to this. And that's pretty much it. And then at the end, once we've done all of this, and every time we find a leaf that has shortest path less than this, we increase the count by 1, right? And then the last step would be to just so the last step would be to just return this count, right? But there is just one caveat there. Since our graph here, we will do it in a way that it doesn't have a direction, which means that this one would have neighbor this one, but this one also would have neighbor this one, right? And so that means we will be counting 2 times, and so we will need to divide by 2. And that's pretty much it, right? So these are the steps for our algorithm, and so right now we can just write it down and make sure it works. So convert the tree into a graph. That's the first step. The second step is find all leaf nodes of the tree, right? And then for each leaf node, we do a BFS. We find any other leaf node that is a neighbor of it, like that is reachable from it, that has the distance between the two less than or equal to the distance that we have. And of course, they have to be different. And if we found such one, we can add to the count plus 1. We can do another pruning here that is usually done with BFS, which is if the current level, or you can call it level or length, is bigger than distance, we can just exit the BFS for that leaf, right? And BFS for that leaf, right? Because there is no point in continuing, because we will only increase the level if we keep going down, right? And so this is the main idea. Now let's code it up and make sure it passes. Our solution here. So first we will need to convert the tree into a graph. We can do DFS to do that. So DFS starting from a node. And we need, of course, the graph map representation here. So that would be just a default dictionary here that is composed of a list. And we check if we have the node. We want to, of course, we want to pass the parent, right? Because we want to say that the node, like let's say 1 has neighbor 3 and 3 has neighbor 1. That's what we want to do. So we want to pass the parent. And since for the first call, which is for the root doesn't have a parent, so we want to just initialize with none if nothing is passed. We could also do something like this. And so we can just say parent is equal to none if nothing is passed. And now our graph would be that node has neighbor parent and parent has neighbor node. If the node is null, we don't want to continue. That's kind of our base case. And here we have node, and we need to recurse on the left child and on the right child as well. So now we have the graph. We did step 1. Which is convert tree to a graph. Next step would be to find all leaf nodes. So for that, we can just go through all the keys in the graph, which are just nodes, right? So we can just say node in graph.keys. And basically check if node doesn't have a left child and node doesn't have a right child. We can just that would mean that it's a leaf, right? So we need first a set of leaves. So let's just declare a set here, and now we can add to that set the node. And now we have the leaves. Now step 3 is BFS for each leaf. So to do that, we are going through the leaf nodes, and we start the normal BFS here. So we will need to create a queue for our BFS. So that would be, we want the node itself, and then we want the level or the length, let's call it here. And then we want to see the nodes that we already seen, we want to keep them in a set so that we don't go over them again and end up with a loop. So we need to a set here, and we can say while queue, we are going to pop from the queue, so we will need to do pop left. This is just normal BFS. We pop from the left. We can pop from the left and push from the right, or we can do the reverse. And so this will give us a node and a length, or a level, if you will. Here actually we could do pop 0 instead, right? To do a pop left, we can use a DQ later on here to be able to do a pop left. And so this we will need to check if the length exceeds the distance, then no need to continue, because if the current level is bigger than the distance, it will only increase, so no need to continue here, right? So we can just break out of this BFS. Now we can go check if we are at a leaf node and the distance, the length, the level is smaller than the or equal to the distance. That means we found two leaf pair nodes that have the property that we are looking for, and we can add that to the count. And so to do that, we need to have the count here equal to 0. And then we can say if the first condition is that it has to be not the same leaf, right? The second condition is it has to be a leaf. So that means not node.left and not node.right. And the last condition is the distance has to be less than or equal to the threshold distance. So less than or equal to distance. If all of this is true, we can add that to the count. And now we can go through the neighbors of the node. There is just one thing we need to do here, because when parent was equal to none, we did add it to the graph. So we can expect some nodes to be null, right? And so we will need to make sure that this is not none, right? And then we need to make sure that we haven't seen it before. So neighbor not in scene. And here we will need to, of course, add the leaf node to the scene set, because we already added it to the queue. Now we can append the neighbor to the queue here. And since this is the next level, the length should increase by 1, right? Or level should increase by 1. This is the same as level. And we need to say that we've seen it, right? Because we added it to the queue, so we've seen neighbor. And that's pretty much it. We can return count here. Now let's run this, make sure these test cases pass. So we have an error here, yep. So we need to make sure node, and because as I said, we had parent which is none here, so we need to make sure that the other way to do this is to check here before appending as well, but this should work as well. So not if node, of course, instead. Here if node as well. Okay, let's see. So we pop here. We make sure the distance is correct. Here we need to divide by 2, of course, since, as I said, the node has a neighbor parent and parent has a neighbor node. So we have 2 nodes, like 2 directions for the same 2 pairs. And so we'll be calculating this 2 times, right, for each pair. And so we need to divide by 2 to make, yeah. And there is still a small issue here. Let's see. Okay, so there is a mistake here, because we need to pass the parent. Sorry about that. So we need to pass, of course, the parent when constructing the graph, so that, yeah, the node can have a neighbor is parent and the parent can have the neighbor as its node. The other error is that not nay here means that the neighbor, we are picking only the null neighbors, which is not what we want. We want to pick only the neighbors that have a value. So if I just rename this neighbor, so we want the neighbors that are not null, right? And we want them to not have been visited before. So those are the 2 errors that we have. Let's run this, and all our test cases pass. We could write more test cases, and this should definitely pass. And so just to summarize this solution here, we are doing BFS to convert the tree to a graph. Then we find the leaf nodes. Then for each leaf node, we do a BFS to find the leaf nodes that have a shortest path from it, all of them that have a short path from it that is smaller than or equal to distance. And we count those, And that's pretty much it. We divide by 2 because we are counting twice, because of the fact that we are having 2 directions included in the graph. And that's pretty much it, I think. Yeah, that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.